So this is the project, and I say this is the essential project to understand memory management and the flaws of memory management. This is the classic case of buffer overflow. This is the most important thing to understand to get all this right. You need a Intel processor. So I'm running an emulated Intel processor on my ARM processor, which I showed you how to make a while ago in the earlier projects. You'll find that back up here, preparing your Linux environment. In here shows you how to do this. So so what I'm going to do is create a vulnerable program, and here it is. Let me just bring it up. I've already got it in here. If I cat pwd.c, here's the main routine. It calls a function called testpw, and if the answer is not 0, it prints fail. It'll only win if it returns 0. But when you go here, it asks you for a password and reads it, but then it doesn't do anything with it. It just always returns 1, so you always fail. You will never execute the win function. It's the developer didn't intend for you to ever get to this win function, but we're going to get there by doing a buffer overflow. And in order to have the buffer overflow work, we define a 10-character password here, and then we accept up to 50 characters from standard in. This is the fundamental flaw of C. Here, I told it to read up to 50 characters, and it doesn't know that I only reserved room for 10. And that's what makes it possible for the buffer overflow to work. So I'm going to compile this. Now, if you follow these instructions, you can do a cross-compilation for 32-bit Intel instead of 64-bit Intel, which is how we're going to start, because 32-bit Intel is simpler and a little easier to understand. So what this does is it compiles the program. The -G means it includes symbols so we can easily debug it. The -M32 means make it 32-bit. The output is going in a file called pwd32, and the input is from pwd.c. So there it goes. Now notice I got some warnings. I just got warnings. It warned that fgets is writing 50 bytes into a region of size 10. So the compiler noticed that this is bad, but it didn't stop me, because it's possible that I had a plan. And I intended this. I defined that 10, then I defined some other things after it, and I chose to deliberately write into them. You can do crazy things like that in C or assembler. It's not a good idea, because other developers will not understand your code and it's likely to break, but the original point of C was to make it possible to write code that did brilliant, clever things at the binary level, which would look funny. So it doesn't stop you, but it does warn you. Anyway, so I can now run it. If I use file, it'll tell me what I've got. And file will tell me I have a 32-bit executable link format, which is Linux executable. So I have a 32-bit Linux executable file, and you run it with /pwd32. It asks me for a password. I put in A, and I fail. And every password I put in will fail. No password is going to be correct. All right. But by the way, let's see if I had a pi object, and it looks like I didn't, so I'm okay. You might have to add this no pi in some systems. Anyway, all right, so now I'm going to try a longer password. I put in this password. Now I get a segmentation fault, which means the program could not finish. It crashed. It did not get to where it would print the fail statement. So this is the clue that I have a buffer overflow, and I have a possibility of taking over the machine, because I managed to break the logic of the program. So now the next thing is, notice every time I run this program, the password address keeps changing. That's address space layout randomization, is what Windows calls it. And that is a security feature, but we want to turn that off for what we're doing here. So I do that with these commands, sudo su minus to become root. And then I put a 0 in this variable called randomize VA space, and then exit. Okay, and now if I just run that password program and give it an A, run it again and give it an A, see, now the password address is the same every time. Now it's not randomly relocating data in memory, which is what we need for this simple attack. Now we're going to use the debugger. GNU debugger in quiet mode, just so it doesn't print a big ugly banner, on pwd32. Since I used the -G command, I can debug it from the C source code. I do not need to read assembler. I can list 1 to 13. And so here's the testpw function where the overflow happens. So you can see here in line 9 is where it tries to return to the program above it. And the buffer overflow happens here in line 8. Line 8 is where I read in data that might be longer than 10. So I want to complete step 8 and then break at line so it doesn't proceed. I want to stop right after line 8 and see what the situation is. So I do that. Now, to get rid of these colors, this helps for making videos and for some screens. It's more readable than usual on my screen here, but often those colors are hard to see, so I get rid of them. All right, so now I'm going to run it and put in a normal variable. I run, and I'll put in 10 A's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it hit the breakpoint. When it hits the breakpoint, I can examine the registers. These are the internal storage in the processor, and the only thing that really matters to me is ESP and EBP. This is the top of the current stack frame, and this is the bottom of the current stack frame. This is where local variables are stored. So the bottom is at 498, and the top is at 480. So I can do examine 12 hexadecimal words starting at ESP. And I know the end of the stack is 498. Let me make this window wider. There. So the way this works, this is 490 0 to 3. This is 494 to 7. This is 498 to A. And this is 49B. So this is the 32-bit word that is at the end of the stack frame. That is the stack frame, that region. And notice these 41s. 41 is the ASCII for capital A. So see, here's capital A's, here's some more capital A's, and some more capital A's. So this is the 10-character password I typed in being stored in the stack frame, and there is no overflow. It had room for 10. I put in 10. Nothing bad happened here. So that means, now the way this works is you have the stack frame here, and when you're done and you return, it looks one past the stack frame here, and this is the return pointer. That tells it where to resume execution. And if you want to understand that, you can disassemble main. And here's the assembly code that runs main. And I just press enter to get more of it. All right, so here we are. It's going to call testpw right here. This is where it calls the testpw function. When it returns, I want it to resume at this command, the next command. So that's the one ending in 55. And if you look here, that's what this does. The bytes are out of order, just to make sure you always have a headache. That's 55. Well, actually, this one's right. 56, 56, 56, 50, 62, 55. That's what it is. This pointer tells it where to resume execution when it returns from this routine. And that's the point. If I put in a longer variable, I can overflow this pointer and take control of the box. So if I continue right now, it's going to run normally, return to where it belongs, and then print fail, return to the routine and finished as normally. But if I do it again with this long value, okay, I run, then I put in this long password. Now it has the breakpoint, so I'm going to look at the registers again. And here you see ESP is 480 and EBP is 498. Notice the stack is still the same size, even though I put in a lot of characters. That's the fundamental problem with C. If it was Java or Python, it would automatically reserve more memory to store whatever you put in. But C is too stupid to do that. It reserved 10 characters, and it won't change it no matter how many you put in. So that means if I look at what's happening on the stack here, then the stack frame still goes only to 498, which is here. So here's the A's, here's the B's, the C's, D's, E's, and you can see I overwrote the stack frame, I overwrote everything, and I overwrote the return pointer, and even went past it here. So now I took the return address that should point to the instruction in main, and now it's pointing to this 46, 46, 47, 47. So if I continue, the program will crash, and here it's telling you the instruction pointer contains this value, and that's invalid because that memory region is not allocated for this program to use. So that's what I said. If you just if you try to refer to memory in a random location, it'll almost always crash because your program only has a small amount of memory allocated to its use, and it does not have this address. And you can tell it if you do info registers. EIP, which is the instruction pointer, now has that crazy value, and that's not one of the reserved memory regions. By the way, if you want to know the reserved memory regions, it's info proc map, I think. Yeah. Here you can see the reserved memory regions for each executable, and these are libraries, and more. Here's the PWD program. Here's the regions it has. They're all starting with 56. So those are the blocks of memory it has for various parts of the program, and that address is not one of them. That's why it fails. So what I've done is I've created a denial of service attack. This long password causes it to crash. What I want to do is execute the win function. So I can disassemble win and get this address. This is the address I want to put in the return pointer. Now, often this address contains unprintable characters like 0b. So I can't just use printed letters. I have to use a little bit of Python to print it. So there's a Python program to start with here. Let's put that in here. I get out of here, and then nano exploit pwd 32, and put in this code. Now, the number one mistake students make is they run this program exactly and it fails on their machine because you have to find the right address for your machine. They aren't all the same. So that's what I want to put here. Let's go back here let's get out of here and go back up here. I want to run the win function. This is the address of the win function now. So I'm going to copy that, and I'm going to put it in here with a comment. Pound makes a comment in Python. There. That's the address I want. Now, you might not be obvious how I chose this prefix and postfix. Let's talk about that a bit. If I go back into the debugger, all right, and I run it, and I feed it that same long entry, which is this one. Okay. Now, here's where it crashes: 46, 46, 47, 47. 41 is A, 42, 43, 44, 45, 46. So the code that ended up in the instruction pointer was the last two F's and the first two G's. That's what this is: 46, 46, 47, 47. So I know that is where I need to put the address of the function I want to go to. And so I want to put in the prefix is everything up to the first two F's. Then go these 4 characters. Now, it's not necessary for this attack, but this is a good habit to always make your input the same total length, because there are more complicated programs where inputs of different length will crash at different points. And you always want to hit the same weak spot. So here you see, let me get rid of the colors to make this more readable. It's minus Y none, I think. Yeah. All right. So here, I put in the prefix up to the first two F's. Then I put in 4 bytes to point to an address, and then I put in enough postfix to keep the total length the same. And you have to put them out of order. So here the lowest, 56, 55, 62, 56, 55. Then the next one should be 62. And the next one should be 0B, which is why you have to use Python, because this one's not printable. That's a form feed or something ridiculous like that. So this will put the right address in where the 2 F's and first 2 G's were. So that's it. Now if I run that, I can run it with Python 3, for example, or I can make it executable. Let's just make it executable. Let me just cat it, exploit there. I did include the shebang line. That's what makes it possible to run I can mod it to be executable. Then I don't need to use Python. I can just run it this way. So I /run it, and it prints out stuff. You got up to 2 F's, then it printed some weird stuff, some of which was not printable, and then it continues. So if I want to see what it looks like, I have to put it in a file like foo. That's output redirection. Now if I do ls-l, the file foo is 40 characters long, and if I want to examine it, the best thing to do is xxd. This will let you examine it in hexadecimal. Since it contains unprintable characters, now I can see 41, 41, 42, 42, and here, after 46, 46 comes 0b, 62, 55, 56. That is the address of the win function. So if I run the program, pwd 32, and I take the input from foo, I win. Okay, redirected to the win function. So I took control of the box and I ran code that the developer did not intend to run. This is a very simple case, but it's the fundamental case to understand a buffer overflow, and you learn a lot about how a program runs this way. You learn how the memory is allocated, how the stack works, where the return pointer is, and so on. So this is the basic condition, and there's a whole lot of extra credit here where you do variations of this, like do it in 64-bit and so on. but it's all the same principle. If you understand the first one, you've understood the essential thing about memory corruption attacks, of which there are a ton, but they're all minor variations on this one. And this is the classic buffer overflow that was responsible for almost all Windows viruses up through Windows XP. So that's an important thing for you to play with, and it shows the point. This is why you want to learn how memory is handled, because unfortunately, memory is handled poorly in C. Almost all software is written in C. There are a lot of mistakes in it, and this is how you understand those mistakes and how they come about. Let me check the Twitch for comments, of which there are none. All right, I'm going to stop this recording.